You have probably heard of Andromeda, you may have even seen it. A faint smudge of light in the autumn sky, visible on clear nights far from city lights. It appears in documentaries, in textbooks, in lists of objects amateur astronomers should observe. It is often called our nearest galactic neighbour. The word neighbour makes it sound close, familiar, something within reach of understanding. But Andromeda is not close, and calling it a neighbour is one of the most profound understatements in all of astronomy. What that small patch of light represents, what it truly is, exceeds the boundaries of human intuition in ways that are difficult to accept even when explained. The numbers are available, the facts are known. But numbers alone do not convey the reality of what Andromeda means. This is not a galaxy you can comprehend by reading its statistics. Distance, size, mass, speed, all of these are accurate. All of them are true, but none of them alone will give you the feeling of what Andromeda actually is. To understand Andromeda is to understand the failure of human scale. It is to recognize that something you can see with your own eyes is so far away, so large, so utterly removed from your existence, that even looking directly at it does not bring you closer to grasping it. This video is not about Andromeda as a catalogue entry. It is about Andromeda as a concept. It is about what happens when you try to truly comprehend the scale of something that is both visible and unreachable. It is about the strange, quiet discomfort that comes from realizing that the universe operates on terms that have nothing to do with you. By the end, you will not know new facts about Andromeda. You will understand what the facts mean, and that understanding changes everything. On a clear night, far from streetlights and the glow of cities, you can see approximately 3,000 stars with your unaided eyes. Most of them are within a few hundred light-years of Earth. Some are closer, just dozens of light-years away. A handful are more distant, perhaps 1,000 light-years out, but even these are neighbours in cosmic terms. They are all part of our galaxy, all members of the same gravitationally bound structure we call the Milky Way. When you look up at the night sky, you are seeing your immediate stellar neighbourhood. Every point of light is a sun, some smaller than our own, some vastly larger, but all of them relatively nearby in the grand scheme of the cosmos. But there is one object visible to the naked eye that does not belong to this neighbourhood. It appears as a faint elongated smudge in the constellation Andromeda, best seen in autumn from the northern hemisphere. It does not look like a star. It looks like a small cloud, a patch of diffuse light that seems out of place among the sharp points of starlight. For centuries, people noticed it. They catalogued it. They called it a nebula, a cloud, something within our own cosmic backyard. They were wrong. That smudge is not a cloud of gas. It is not a nearby stellar nursery. It is not part of the Milky Way at all. It is another galaxy entirely. It is called Andromeda, or M31, and it contains roughly 1 trillion stars. You're seeing all of them at once, compressed into that faint patch of light. You're seeing an entire galaxy, a structure so massive and so distant that it defies the scale of everything else visible in the night sky. Every other naked eye object you can see is either in our solar system or part of our own galaxy. Andromeda stands alone as the only extragalactic object visible without optical aid to most human observers. When you look at Andromeda, you're not looking at something a few hundred light-years away. You're looking at something 2.5 million light-years away. The light entering your eyes left Andromeda before modern humans existed. It travelled through empty space for longer than our species has been on Earth. It crossed a void so vast that nothing human-made has ever traversed even a millionth of that distance. And yet, you can see it. Without a telescope, without instruments, without any technology at all, you can see it. This is deeply strange. Most objects in the universe are invisible to us, hidden by distance or dimness or the limitations of human vision. We cannot see individual stars in other galaxies without powerful telescopes. We cannot see planets around other stars. We cannot see the faint background radiation left over from the Big Bang. We cannot see most of what exists. The universe is largely invisible to human eyes, not because it is not there, but because we are simply not equipped to perceive it. Our eyes evolved to see predators and prey, to navigate terrain, to recognize faces. They did not evolve to see across intergalactic distances, and yet we can see Andromeda. We can see an entire galaxy, billions of times farther away than any individual star in our own sky, simply by looking up. The reason you can see it is not because Andromeda is close. It is because Andromeda is enormous. Its physical size is so great that even across 2.5 million light-years, it still subtends enough angular width in the sky to be visible. If your eyes were slightly more sensitive to faint light, Andromeda would appear larger than the full moon. It would dominate the autumn sky, a vast oval of diffuse glow stretching across several degrees of your field of view. The full structure of Andromeda, if it were bright enough to see in its entirety, would span roughly 6 times the width of the full moon. But your eyes are not that sensitive, so you see only the bright central core, the densest concentration of stars at Andromeda's heart. You see perhaps 10% of its true extent. Every photon of light that enters your eye from Andromeda has been travelling for 2.5 million years. Each one left the surface of a star in that distant galaxy, when Earth was in the Pliocene epoch, when early hominids were beginning to walk upright in Africa, when the continents were in slightly different positions than they are now. Those photons crossed the intergalactic void, passing through near-perfect vacuum, undeflected and undisturbed, until they happened to intersect with the tiny aperture of your pupil. Most of the photons emitted by Andromeda will never hit anything. They will travel outward forever, expanding into the universe, destined to pass through empty space for eternity. But a few, an incomprehensibly small fraction, happen to reach Earth, and an even smaller fraction happen to reach you. This means that when you see Andromeda, you are not seeing it as it is, you're seeing it as it was. You're looking backward through time. The Andromeda you observe is ancient. The stars you see may no longer exist. Some may have exploded as supernova millions of years ago. Some may have died quietly, fading into white dwarfs or collapsing into neutron stars. New stars have certainly been born in Andromeda since the light you see was emitted. Entire stellar generations have come and gone. Planets have formed. Planetary systems have been destroyed. Whatever exists in Andromeda right now, at this very moment, is completely unknown to you. It will remain unknown for another 2.5 million years, because that is how long it will take for light from present-day Andromeda to reach Earth. You're separated from Andromeda not just by distance, but by time. And yet, despite this immense distance, despite the incomprehensible age of the light reaching your eyes, Andromeda is considered our nearest major galactic neighbour. It is the closest large galaxy to the Milky Way. There are smaller galaxies closer to us, dwarf galaxies, satellite galaxies orbiting our own, but Andromeda is the nearest galaxy of comparable size. If this is our neighbour, if this is what nearby means on a galactic scale, then the universe is far more isolated, far more empty than human intuition can accept. The word neighbour implies proximity, closeness, the ability to interact. But there is no interaction possible across 2.5 million light years, not in any time frame that matters to human life or human civilization. You can see Andromeda because it is bright. You can see it because it is massive. You can see it because it is one of the very few galaxies close enough and large enough to be visible without technology. But seeing it does not mean understanding it. The light reaches you, but the reality of what you are seeing does not. Your brain interprets it as a smudge, as something small and distant, as an object that fits comfortably into the category of things in the night sky. It does not feel like what it is. It does not feel like 1 trillion stars. It does not feel like 2.5 million light years. It does not feel impossible. When ancient humans looked up and saw that faint smudge, they had no idea what they were looking at. They could not have known. The very concept of a galaxy did not exist. The idea that there were other islands of stars, other massive collections of suns separated from our own by unimaginable distances, was not even imaginable. They saw it, they noted it, and they moved on. It was just another feature of the night sky, no more significant than any other patch of light. It took thousands of years of observation, centuries of technological development, and decades of careful measurement before humanity finally understood what that smudge was. And even now, knowing what it is, understanding what it represents, the smudge still looks the same. It still appears small, it still appears insignificant. This is the paradox of Andromeda. It is visible but incomprehensible. It is the farthest thing you can see with your naked eye, and yet it appears as nothing more than a faint blur. It contains 1 trillion suns, and yet it occupies less space in your visual field than a single star. It is both present and absent, both near and impossibly far. You can point to it in the sky, You can photograph it, you can observe it, but you cannot grasp it. The scale is too large, the distance is too great. The reality of what you're seeing exceeds the capacity of human perception to process, and this is only the beginning. Light moves at 299,792 kilometers per second. In human terms, this is incomprehensibly fast. If you could travel at the speed of light, you could circle the Earth's equator more than 7 times in a single second. You could reach the moon in just over 1 second. You could travel from the sun to Earth in 8 minutes and 20 seconds. Nothing in human experience moves at anything close to this speed. The fastest aircraft ever built, the North American X-15, reached a maximum speed of about 7,200 kilometers per hour. At that speed, it would take roughly 4 months of continuous flight to reach the moon. Light makes the same journey in less time than it takes you to blink. But the speed of light, despite being the fastest possible speed in the universe, is not fast enough to make cosmic distances feel small. When you begin to measure distances between stars, between galaxies, between structures in the universe, the speed of light becomes a reminder of how vast everything truly is. Light from the sun takes 8 minutes to reach Earth. Light from the nearest star system, Alpha Centauri, takes 4 years. Light from the center of our galaxy takes approximately 26,000 years, and light from Andromeda takes 2.5 million years. This means that when you look at Andromeda, you're seeing light that began its journey 2.5 million years ago. You're not seeing Andromeda as it exists now. You're seeing Andromeda as it existed in the deep past, long before human civilization, long before anatomically modern humans, long before anything resembling human culture or language or thought. The light you see left Andromeda when Earth was home to early hominids, species like Australopithecus, creatures that walked upright but had brains a third the size of modern humans. They had no language. They had no tools beyond the simplest stone implements. They had no conception of the sky, no understanding of stars, no capacity to wonder what that faint smudge of light above them might be. While that light was travelling toward Earth, the entire story of human evolution unfolded. Australopithecus gave way to early Homo species. Homo habilis emerged, then Homo erectus. Stone tools became more sophisticated. Fire was mastered. Homo heidelbergensis appeared, then Neanderthals, then Denisovans, and finally, roughly 300,000 years ago, anatomically modern humans emerged in Africa. The light from Andromeda was still travelling. It had crossed more than 2 million light-years by this point, but it still had 500,000 years to go. Modern humans spread across Africa. They developed language, art, ritual, culture. They began to paint on cave walls, to carve figurines, to bury their dead with ceremony. They left Africa and spread into Europe, into Asia, into Australia. They survived ice ages. They domesticated plants and animals. They built the first permanent settlements. They invented agriculture, writing, mathematics, astronomy. They built cities, empires, civilizations. And all the while, the light from Andromeda continued to travel through the void, unaffected by any of this, indifferent to the rise and fall of species and cultures, moving at constant speed through empty space. By the time that light finally reached Earth, humans had already looked up at the night sky and wondered what they were seeing. They had already created myths and stories to explain the stars. They had already begun to map the heavens, to track the movements of planets, to predict eclipses. And when they saw that faint smudge in the constellation Andromeda, they noted it, catalogued it, and assumed it was something nearby. They had no way of knowing that the light entering their eyes was older than their entire species. This is what 2.5 million light-years means. It does not just mean distance, it means time. It means separation not just in space, but in history. The Andromeda you see is not the Andromeda that exists. The Andromeda that exists right now at this very moment is unknowable to you. If something dramatic happened in Andromeda today, if a supernova exploded, if a star was torn apart by a black hole, if an entire region of the galaxy suddenly brightened, you would not know about it for 2.5 million years. By the time the light from that event reached Earth, humanity might not even exist anymore. Our species might have evolved into something else, or gone extinct, or spread across the galaxy, or vanished entirely. The light would arrive regardless, indifferent to whether anyone was here to see it. This is true for everything you see, but the effect is usually negligible. When you look at another person, you're seeing them as they were a few billionths of a second ago, the time it takes for light to travel from them to your eyes. When you look at a mountain a kilometre away, you're seeing it as it was a few microseconds ago. When you look at the moon, you are seeing it as it was 1.3 seconds ago. When you look at the sun, you are seeing it as it was 8 minutes ago. These delays are small enough that they do not matter. The sun you see is effectively the sun that exists. The person you see is effectively the person that exists. But when you look at Andromeda, the delay is no longer negligible. It is no longer a technicality. It is fundamental. The Andromeda you see is ancient history. It is a ghost, a memory, an image of something that no longer exists in the form you are observing. Stars have lived and died in the time it took for that light to reach you. The structure of the galaxy has changed. New spiral arms may have formed, old ones may have dissipated. The supermassive black hole at Andromeda's centre has consumed millions of solar masses of material since the light you see was emitted. The entire galaxy has rotated multiple times. Everything is different now, but you cannot see the difference. You can only see the past. And yet, we call Andromeda our neighbour, we describe it as nearby. We point to it in the sky and say, there it is, just over there in that direction. But direction is not the same as proximity. You can point towards something that is impossibly far away. You can aim a telescope at something that no longer exists in the form you're observing. The act of seeing does not bring you closer, it only confirms the separation. The light from Andromeda will continue to arrive. Every night, photons that have been travelling for 2.5 million years will reach Earth. Some will strike telescopes, some will strike human eyes, some will strike nothing at all, absorbed by the atmosphere or scattered into space. The light does not care. It is not trying to reach you. It is simply moving, as light does, expanding outward in all directions from every star in Andromeda, filling the universe with information about a galaxy that no longer exists in the form being transmitted. And this is just Andromeda. This is the closest large galaxy. This is our neighbour. When you look deeper into space, at galaxies billions of light years away, you're looking billions of years into the past. You're seeing galaxies as they were when the universe was young, when Earth did not exist, when the sun had not yet formed. You're seeing light that has been travelling for longer than our planet has existed. The delay becomes so extreme that the objects you're observing are not just different from how they appear, they may no longer exist at all. They may have collided with other galaxies, been torn apart by gravitational forces, or simply faded into darkness as their stars died and no new ones formed. But Andromeda is close enough that it still exists. The galaxy you see is old, yes, but the galaxy itself is still there, still intact, still rotating, still forming stars. The light is a message from the past, but the sender still exists in the present. You are separated by time, but not by existence. Andromeda is real, even if you cannot see it as it is. This is what 2.5 million light-years means. It means that when you see Andromeda, you are looking at history. You are receiving a transmission from the distant past, carried across the void by particles of light that have been travelling since before your species existed. And that light will keep coming, night after night, year after year, century after century, carrying the same ancient message, until something changes. Until the distance closes. Until Andromeda is no longer a neighbour observed from afar, but something else entirely. When you try to comprehend the size of something, you begin with comparisons. You measure one thing against another. A building is taller than a person. A mountain is taller than a building. The atmosphere extends higher than the tallest mountain. These comparisons work because the scales are related. You can imagine walking from the base of a mountain to its peak. You can visualize stacking buildings on top of each other until they reach the height of the atmosphere. The numbers may be large, but they remain within the realm of human understanding. Andromeda's width is not within that realm. The galaxy measures approximately 220,000 light-years across. To understand what this means, you need to start with something familiar, and then watch that familiarity collapse under the weight of scale. Begin with Earth. The diameter of Earth is about 12,700 kilometers. If you could somehow travel around the entire circumference of the planet at highway speed, driving continuously without stopping, it would take you roughly 2 weeks. Most people have driven for 2 weeks cumulatively in their lives, perhaps on road trips or commutes. The scale of Earth is large, but it is comprehensible. You can drive across it. You can fly around it in less than 2 days. You can hold the entire planet in your mind as a complete object. Now consider the Sun. The Sun's diameter is about 1.4 million kilometers, roughly 109 times wider than Earth. You could line up 109 Earths side by side across the face of the Sun. If Earth were a marble, the Sun would be a sphere nearly as tall as a person. This is still comprehensible. You can visualize it. You can imagine 109 marbles in a row, and then imagine scaling that up. The Sun feels large, but it feels finite. It is a discrete object with clear boundaries. You can point to where it begins and where it ends. But the Sun is nothing compared to the distances between stars. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at 299,792 kilometers per second, which equals roughly 9.46 trillion kilometers. Proxima Centauri is therefore about 40 trillion kilometers away. If you were to build a scale model where the Sun was the size of a marble, roughly 1 centimeter across, Proxima Centauri would be another marble located about 270 kilometers away. The distance between stars is not empty space punctuated by occasional objects. It is almost entirely empty space with objects so rare and so distant from each other that they might as well not exist. And this is just the distance between 2 neighbouring stars in our own galaxy. Andromeda is not measured in distances between stars. It is measured in the total span of hundreds of billions of stars spread across a structure so large that light itself takes 220,000 years to cross from one side to the other. If you could travel at the speed of light, the fastest speed possible in the universe, it would still take you 220,000 years to journey from one edge of Andromeda to the other. Civilizations could rise and fall in that time. Species could evolve and go extinct. Entire epochs of planetary history could pass while you are still crossing a single galaxy. To put this in human terms is nearly impossible, but consider this. If you were to travel across Andromeda at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, which reached a maximum speed of about 163 kilometers per second relative to the Sun, it would take you roughly 400 million years to cross the galaxy. That is longer than the time since the first vertebrates crawled onto land. It is longer than the existence of dinosaurs. It is longer than the existence of most complex life on Earth. You would begin your journey across Andromeda in a universe that had never known forests or flowers or animals with backbones, and you would still be travelling when humans evolved, rose, built civilizations, and potentially disappeared. And even this comparison fails because it still treats Andromeda as if it were a single object, a thing you could cross. But Andromeda is not a thing. It is a collection, a structure made of individual stars separated by distances so vast that most of them will never interact with each other. The average distance between stars in Andromeda's disk is several light-years. If you were standing on a planet orbiting a star in Andromeda and you looked up at the night sky, you would see other stars, just as we see stars from Earth. But those stars would still be light-years away. You would still be isolated, still separated by emptiness, still alone in a local bubble of space that felt as empty as the space around our own Sun. This is where the concept of width begins to break down. Width implies a measurement from one edge to another, a span you can understand by imagining movement across it. But Andromeda is not a solid object. It has no edges in the traditional sense. Its boundary is gradual, a slow fade from densely populated regions to sparsely populated regions to nearly empty space. There is no clear line where Andromeda ends and intergalactic space begins. Stars thin out, distances between them increase, and eventually you find yourself in the void between galaxies. But there is no wall, no border, no definitive edge. Width becomes a statistical measure, a definition based on where star density falls below a certain threshold, but not a physical thing you can point to. And yet, even with this ambiguity, the numbers remain staggering. Andromeda is more than twice as wide as the Milky Way. If you could see both galaxies from an external vantage point, Andromeda would dominate. It would appear vast, sprawling, a massive spiral of stars dwarfing our own galaxy. But from Earth, from inside the Milky Way, Andromeda appears small. It appears as a faint smudge. The width that is incomprehensible in absolute terms becomes almost invisible in angular terms. This is the deception of distance. Something can be enormous, and still appear tiny. Something can span 220,000 light-years and still fit within the width of your thumb held at arm's length. If Andromeda were closer, if it were only a few thousand light-years away instead of 2.5 million, it would dominate the night sky. It would be terrifyingly large, an immense spiral structure filling your vision, bright enough to cast shadows impossible to ignore. You would see individual stars within it, clusters of stars, nebulae, the bright core, the dark dust lanes, all of it visible in overwhelming detail. But it is not close, it is far, and distance compresses everything. The width that took light 220,000 years to cross appears to your eyes as something barely noticeable, something you might miss entirely if you were not looking for it. This compression creates a cognitive dissonance. You know Andromeda is large. You know the numbers. You understand that 220,000 light-years is an incomprehensible distance. But your eyes tell you something different. Your eyes tell you that Andromeda is small, faint, insignificant. Your brain cannot reconcile these two realities. The intellectual understanding and the visual perception do not match. You are forced to hold two contradictory ideas in your mind at the same time. Andromeda is enormous, and Andromeda appears tiny. Both are true, neither one cancels out the other, and this is just the width of the galaxy itself. This does not account for Andromeda's halo, the vast cloud of gas and dark matter that surrounds the visible galaxy. The halo extends far beyond the spiral disk, reaching out hundreds of thousands of light-years in all directions. If you could see the halo, if it were bright enough to be visible, Andromeda would appear even larger. It would stretch across vast regions of the sky, overlapping with other structures, blending into the cosmic web of matter that connects all galaxies. But the halo is invisible. It does not emit light. It can only be detected through its gravitational effects, through the way it bends light from more distant objects, through the motion of stars at the edges of the visible galaxy. The width you see is not the true width. The true width is larger, more diffuse, less defined. When astronomers measure Andromeda's width, they are making a choice about where to stop counting. They are deciding at what point the density of stars or gas or matter becomes low enough to be considered outside the galaxy. This is a practical decision, not a physical one. The universe does not care where we draw the line. Stars do not suddenly stop existing at some arbitrary boundary. The galaxy simply fades, gradually, imperceptibly, until you're no longer in it. The width is real, but the edges are not. This is true for all galaxies, but it is especially true for something as large as Andromeda. The width is so great that it exceeds human intuition. You cannot visualize it. You cannot hold it in your mind as a complete image. You can understand it intellectually, you can calculate it mathematically, but you cannot feel it. The numbers are too large. The scale is too vast. The concept of width, which works perfectly well for buildings and mountains and planets, fails when applied to galaxies. You are left with a measurement that is accurate but meaningless, true but incomprehensible. And yet, Andromeda is not even particularly large as galaxies go. There are galaxies much wider, much more massive, much more sprawling. There are elliptical galaxies that contain trillions of stars spread across hundreds of thousands of light-years. There are galaxy clusters that span tens of millions of light-years. Andromeda is large, yes, but it is not extraordinary. It is simply the closest example of something that human minds were never equipped to comprehend. It is 220,000 light-years wide, and that width is both a fact and an impossibility. Andromeda contains approximately 1 trillion stars. This is the number most commonly cited, the figure that appears in textbooks and documentaries and articles. 1 trillion. It is written as 1 followed by 12 zeros. It is a number that appears frequently in discussions of national debt, of global economics, of computational operations performed by modern processors. It is a number humans have learned to use, to calculate with, to reference casually. But using a number is not the same as understanding it. Consider what 1 trillion means in terms you can actually grasp. If you were to count to 1 trillion, counting one number per second without stopping, it would take you approximately 31,700 years. You would need to count continuously, every second of every day, for longer than the entire span of recorded human history. You would begin counting before the construction of the pyramids, before the invention of writing, before the first cities were built, and you would still be counting now. And even then, you would not be finished. But stars are not grains of sand. Stars are not passive, inert particles. Each one is a nuclear furnace, a massive engine of energy production. Each one emits light, heat, radiation. Each one influences the orbits of everything around it. Each one lives and dies on timescales of millions or billions of years. The grains of sand on a beach do nothing. They sit there, moved occasionally by wind or water, but fundamentally static. Stars are dynamic. They evolve, they change, they explode, and there are 1 trillion of them in Andromeda, all evolving simultaneously, all changing, all contributing to the overall structure and behaviour of the galaxy. This means that at any given moment, stars are being born in Andromeda. Gas clouds are collapsing under their own gravity, heating up, reaching the temperatures and pressures necessary for nuclear fusion to begin. New stars are igniting, and at the same time other stars are dying. Massive stars are exploding as supernovae, scattering their material across the galaxy, seeding the interstellar medium with heavy elements. Smaller stars are swelling into red giants, shedding their outer layers, fading into white dwarfs. The galaxy is not static, it is a living system, constantly recycling material, constantly transforming itself. And all of this is happening across 1 trillion stars. The number of stars being born each year in Andromeda is estimated to be less than 1 per year, far lower than the Milky Way's rate of a few stars per year. Andromeda is an older galaxy, more evolved, with less available gas for new star formation. But even at a low rate, over billions of years, the cumulative number of stars that have been born, lived and died in Andromeda is staggering. Generations of stars have come and gone. The galaxy you see now is not the galaxy that existed a billion years ago. The stars have changed. The distribution has changed. The structure has changed, but the count remains roughly the same, 1 trillion. This number also represents mass. Each star has mass, and the total mass of all the stars in Andromeda is approximately 1.5 trillion times the mass of the Sun. But even this is not the total mass of the galaxy. Most of the mass in Andromeda is not in stars. It is in dark matter, an invisible substance that does not emit light, does not interact with electromagnetic radiation, and can only be detected through its gravitational effects. The dark matter halo surrounding Andromeda contains far more mass than all the visible stars combined. Estimates suggest the total mass of Andromeda, including dark matter, is somewhere between 1 and 2 trillion solar masses. The exact number is uncertain, but the scale is clear. Andromeda is not just a collection of stars. It is a gravitational structure held together by mass you cannot see, mass that outweighs everything you can see. And yet, when you look at Andromeda, you see only the stars. You see only the visible matter, the light-emitting fraction of the galaxy. The dark matter is invisible. The gas between the stars is mostly invisible. The black holes, the neutron stars, the white dwarfs, all of these are too faint or too small to see individually from 2.5 million light-years away. You see 1 trillion stars compressed into a faint smudge of light, and you miss the vast majority of what is actually there. This is the mass inventory of Andromeda. 1 trillion stars, each one a sun, trillions of planets, each one a world, vast clouds of gas and dust, a supermassive black hole at the centre, an enormous halo of dark matter, all of it held together by gravity, all of it rotating, all of it evolving. The numbers are so large that they lose meaning. You can write them down, you can calculate with them, but you cannot feel them. You cannot grasp what 1 trillion stars actually means. Your brain was not built for it. Human intuition does not operate at this scale, and this is just one galaxy. This is just Andromeda. There are hundreds of billions of galaxies in the observable universe, many of them containing similar numbers of stars. The total number of stars in the universe is estimated to be on the order of 10 to the 24th power, a number so large that it exceeds even the number of grains of sand on Earth. It exceeds the number of atoms in a human body. It approaches the total number of atoms in all of Earth's oceans, and each one of those stars is a sun, a massive object, a real thing occupying real space. But you are here, looking at Andromeda, looking at 1 trillion of them, and you cannot count them, you cannot visit them, you cannot know them. All you can do is acknowledge that they exist, that they are real, and that their number exceeds your capacity to understand. Andromeda is moving toward us. This is not a metaphor or an approximation. It is a precise, measurable fact. The galaxy is approaching the Milky Way at approximately 110 kilometers per second. This is fast by human standards. It is roughly 400,000 kilometers per hour, more than 300 times the speed of sound, faster than any human-made object has ever traveled. If you could move at this speed, you could travel from New York to Los Angeles in less than 12 seconds. You could circle the Earth in under 2 minutes. You could reach the Moon in just over an hour. And yet, despite this enormous velocity, Andromeda's approach feels slow. It feels patient. It feels like nothing at all. The reason is simple. The distance involved is so vast that even speeds measured in hundreds of kilometers per second become negligible. Andromeda is 2.5 million light-years away, and it is closing that gap at 110 kilometers per second. At this rate, it will take approximately 4 billion years for the two galaxies to collide. 4 billion years. That is nearly as long as Earth has existed. It is longer than the entire history of complex life on our planet. It is a timescale so immense that it renders the speed irrelevant. Consider what 110 kilometers per second means in practical terms. Andromeda travels roughly 9.5 million kilometers every day. That is 25 times the distance from Earth to the Moon, covered in a single day. Over the course of a year, Andromeda moves approximately 3.5 billion kilometers closer to the Milky Way. That is more than twice the distance from the Sun to Neptune. If you could watch Andromeda's approach in real time, if you could somehow perceive the change in distance directly, it would seem extraordinarily fast. Billions of kilometers per year is not slow by any conventional measure, but conventional measures do not apply. The distance between Andromeda and the Milky Way is approximately 2.5 million light-years, which translates to about 23.6 trillion kilometers. Andromeda's annual progress of 3.5 billion kilometers represents a fractional change of 1 part in 7 quadrillion. If the distance to Andromeda were represented as a meter stick, Andromeda's yearly movement would be less than the width of a single atom. The speed is real, the motion is real, but the scale makes it invisible. This is the strange paradox of cosmic motion. Everything in the universe is moving. Stars orbit the centers of galaxies. Galaxies move through space. Galaxy clusters drift relative to each other. The expansion of space itself carries distant galaxies away from us at speeds that eventually exceed the speed of light. Motion is constant, universal, unceasing, but most of it is imperceptible. Most of it happens on timescales and distance scales that human perception cannot access. Andromeda is hurtling toward us at a speed that would tear any physical object apart, and yet from our perspective, it appears motionless. Astronomers measure Andromeda's velocity using the Doppler effect, the same phenomenon that causes the pitch of a siren to change as it moves past you. When an object emitting light moves toward you, the wavelengths of that light are compressed, shifted toward the blue end of the spectrum. When it moves away, the wavelengths are stretched, shifted toward the red. By examining the spectrum of light from Andromeda, by identifying specific absorption lines created by elements in the stars and gas of the galaxy, astronomers can measure how much those lines are shifted. The shift tells them the velocity. Andromeda's light is blue shifted. It is moving toward us. This is unusual. Most galaxies in the universe are redshifted. Most galaxies are moving away from us, carried by the expansion of space itself. The farther away a galaxy is, the faster it recedes. This is Hubble's law, the observational foundation of the Big Bang theory, the evidence that the universe is expanding. But Andromeda is close enough that the expansion of space between us is negligible. The local gravitational attraction between Andromeda and the Milky Way is stronger than the expansion. Gravity wins. The two galaxies are bound to each other, falling toward each other, destined to merge. But the approach is not simple. Andromeda is not moving directly toward the Milky Way in a straight line. It has tangential motion as well, motion perpendicular to the line of sight. The 110 kilometers per second is only the radial velocity, the component of motion directed toward or away from us. The total velocity is somewhat higher, perhaps 130 kilometers per second when all components are included. This means Andromeda is not going to hit us head-on. It is going to pass by, swing around, interact gravitationally, and eventually merge in a complex dance that will take billions of years to complete. The merger will not be a collision in the traditional sense. Galaxies are not solid objects. they're mostly empty space. The distance between stars within a galaxy is so vast that when two galaxies merge, the stars themselves almost never collide. They pass through each other, their trajectory is altered by the shifting gravitational field, but direct impacts are extraordinarily rare. What does collide is the gas. Clouds of interstellar gas slam into each other, compress, heat up, and trigger waves of new star formation. The shapes of the galaxies distort, spiral arms are torn apart, stars are flung into new orbits. The supermassive black holes at the centres of both galaxies eventually spiral inward and merge into a single, even more massive black hole. The end result is a new galaxy, larger than either of the originals, but fundamentally different in structure. Spiral galaxies like Andromeda and the Milky Way become elliptical galaxies after merging, their organised rotation disrupted into random stellar orbits. But all of this is still 4 billion years away. The approach is happening now, but the consequences are distant. By the time Andromeda and the Milky Way begin their final merger, Earth will likely be uninhabitable. The Sun will have brightened as it ages, increasing in luminosity, heating Earth's surface, evaporating the oceans, destroying the atmosphere. Life as we know it will be gone. Humanity, if it still exists in any form, will have long since left Earth or evolved into something unrecognisable. The merger of Andromeda and the Milky Way will be a cosmic event witnessed by no one from Earth, because Earth as a living world will no longer exist. And yet the motion continues. Andromeda moves closer every second. Right now, as you read this, the distance is decreasing. It is decreasing by 110 kilometers every second, 400,000 kilometers every hour, 9.5 million kilometers every day. The motion is real. The approach is inevitable. Gravity does not stop. It does not pause. It pulls constantly, remorselessly across millions of light years of space, drawing the two galaxies together at a speed that is both impossibly fast and infinitely slow. This raises a question about what speed actually means at cosmic scales. On Earth, speed is meaningful because distances are small and timescales are short. You can drive across a city in an hour. You can fly across a continent in a few hours. You can measure your progress, see the landscape change, feel the movement. But when the distance is 2.5 million light years and the timescale is 4 billion years, speed becomes abstract. Andromeda is moving toward us faster than a bullet, faster than a rocket, faster than anything humans have ever built, and yet it will take longer than the age of Earth to arrive. The speed is immense, but the distance is so much more immense that the speed feels negligible. This is true for all motion in the universe. Stars orbit the galactic centre at hundreds of kilometers per second, but their orbits take hundreds of millions of years to complete. Galaxies move through space at thousands of kilometers per second, but the distances between them are so vast that their positions barely change over the span of human history. The universe is full of motion, full of speed, full of kinetic energy, but almost none of it is perceptible on human timescales. We live in a universe that is dynamic and changing, but we experience it as static and unchanging. The speeds are real, but they are hidden by the scale. Andromeda's speed of 110 kilometers per second is also a measure of gravitational potential energy, being converted into kinetic energy. The two galaxies are falling toward each other, accelerating slowly as they draw closer. The speed will increase over time. By the time the galaxies are close enough to begin seriously interacting, they will be moving faster. The approach will accelerate. The final stages of the merger will be relatively quick, astronomically speaking, perhaps only a few 100 million years from first contact to final coalescence. But we are not in the final stages. We are still in the slow approach, the long fall, the patient descent across a void that dwarfs both galaxies. And throughout this approach, Andromeda remains visible in the night sky. It remains a faint smudge, unchanged in appearance, showing no sign of motion. You can observe it tonight and observe it again in a year, and it will look exactly the same. The motion is invisible, the speed is hidden. Only through careful measurement, through spectroscopy and Doppler shifts and mathematical calculation, can the approach be detected. The human eye sees nothing. The human lifetime is too short. The motion is too slow, or rather the distance is too vast for the motion to register. This is what 110 kilometers per second means at a distance of 2.5 million light years. It means everything and nothing. It means Andromeda is hurtling toward us at a speed that defies human comprehension, And it also means that the galaxy will remain essentially motionless in our sky for millions of years. Both statements are true. Both are accurate descriptions of reality. The contradiction is not in the universe. It is in our intuition, in our inability to hold both the speed and the distance in our minds at the same time. Andromeda is approaching. The distance is closing. The collision is inevitable. But it is not urgent. It is not soon. It is patient, slow, cosmic. The speed is immense, but the timescale is more immense, and so Andromeda hangs in the sky, a faint smudge of ancient light, moving toward us faster than a bullet and appearing to move not at all. 4 billion years. This is the estimated time until Andromeda and the Milky Way begin their merger. 4 billion years from now. The number is easy to write, easy to say, but almost impossible to comprehend. It is a span of time so vast that it erases context, obliterates comparison, and renders human timescales meaningless. To understand what 4 billion years means, you must first understand what has already happened in 4 billion years. 4 billion years ago, Earth was a fundamentally different world. The planet had only recently solidified from the molten chaos of its formation. The surface was still hot, still geologically violent, covered in volcanic activity and bombarded by asteroids. The atmosphere was toxic, composed primarily of nitrogen, carbon dioxide, methane, and water vapor. There was no oxygen. There were no continents as we know them. The oceans had just begun to form as the planet cooled enough for water vapor to condense into liquid, and life, if it existed at all, was limited to single-celled organisms, simple bacteria, perhaps not yet even photosynthetic. From that point to now, everything happened. Life evolved from single cells into complex multicellular organisms. Photosynthesis developed, filling the atmosphere with oxygen, poisoning most of the early life forms but creating conditions for everything that followed. Continents formed, drifted, collided, separated. Oceans rose and fell. Ice ages came and went. The first animals appeared in the oceans roughly 600 million years ago. Plants colonized the land 450 million years ago. Dinosaurs emerged, thrived for over 160 million years, and went extinct. Mammals survived, diversified, and eventually gave rise to primates. Primates gave rise to hominids. Hominids gave rise to humans. And humans, anatomically modern humans, have existed for only the last 300,000 years, a fraction of a percent of the total timeline. All of this, the entire history of complex life on Earth, the rise and fall of countless species, the formation of mountains and the erosion of continents, the evolution of intelligence and consciousness and civilization, all of this happened in less time than it will take for Andromeda to reach us. The time between now and the merger is longer than the time between the formation of Earth and now. It is a complete planetary lifetime. It is enough time for a world to be born, to evolve life, to develop intelligence, to build civilizations, and to die. And this raises an uncomfortable question. What will exist in 4 billion years? The answer is uncertain, but some things are predictable. The Sun will still exist. It is a main sequence star with a total lifespan of approximately 10 billion years, and it is currently about 4.6 billion years old. In 4 billion years, it will be 8.6 billion years old, approaching the end of its main sequence lifetime but not yet finished. However, it will be significantly brighter. Stars increase in luminosity as they age, fusing hydrogen into helium, gradually increasing their core temperature and energy output. In 4 billion years, the Sun will be approximately 40% more luminous than it is today. This additional luminosity will have catastrophic consequences for Earth. The increased solar radiation will heat the planet's surface, accelerating the evaporation of water. Water vapor is a greenhouse gas, and as more water enters the atmosphere, the greenhouse effect will intensify, trapping more heat, evaporating more water, creating a runaway feedback loop. The oceans will boil away, the atmosphere will thicken with steam and carbon dioxide. Surface temperatures will rise to hundreds of degrees. Earth will become uninhabitable, a scorched, lifeless rock orbiting a brightening sun. This process may begin as early as 1 billion years from now. By 4 billion years, it will be long complete. So when Andromeda arrives, Earth will be dead. The oceans will be gone. The atmosphere will be thin or absent. The surface will be baked, sterile, devoid of life. there will be no one here to witness the merger. There will be no forests, no animals, no cities, no remnants of human civilization. If humanity still exists, it will exist elsewhere, on other worlds, in other star systems, perhaps in other galaxies. Earth will be a tomb, a relic, a planet that once supported life but can no longer. But the galaxy itself will still be here. The Milky Way will still exist, still rotating, still containing hundreds of billions of stars, and Andromeda will have crossed the void, closed the distance, and arrived. The first stages of the merger will begin. The two galaxies will not collide directly. They will pass through each other, their stars threading through the gaps between each other's stars, almost never colliding because the distances between stars are so vast. But the gravitational interaction will be profound. The shapes of both galaxies will distort. Tidal forces will stretch and pull at the spiral arms. Stars will be flung into new orbits, some ejected entirely from the merged system, cast out into intergalactic space to wander alone forever. The gas clouds in both galaxies will collide. Unlike stars, gas clouds are diffuse and large, and when they slam into each other, they compress, heat, and trigger bursts of star formation. The merger will light up with new stars, bright blue giants born from the compressed gas, burning hot and dying quickly in supernova explosions. The night sky, if anyone were around to see it, would be spectacular. New stars would appear in vast numbers, nebulae would glow, supernova remnants would shine. The galaxy would be transformed, chaotic, beautiful, violent. After the initial pass-through, the two galaxies will not separate. Gravity will pull them back together. They will swing around each other, losing energy to gravitational radiation and tidal interactions, spiraling inward. The process will repeat, multiple passes, each one bringing the galaxies closer, each one further disrupting their structures. The spiral arms will be destroyed entirely, torn apart by the repeated gravitational disturbances. The organized rotation of both galaxies will be randomized into chaotic stellar orbits. Over the course of perhaps 1 billion years, the two galaxies will merge completely into a single elliptical galaxy, a smooth, featureless distribution of stars with no remaining spiral structure. The supermassive black holes at the centers of both galaxies will also merge. The Milky Way's central black hole, Sagittarius A star, has a mass of about 4 million solar masses. Andromeda's central black hole is larger, perhaps 100 million solar masses or more. As the galaxies merge, these black holes will spiral inward, drawn together by gravity, losing energy as they emit gravitational waves. Eventually, they will collide and coalesce into a single black hole with a combined mass of over 100 million solar masses. The merger of the black holes will release an enormous amount of energy in the form of gravitational waves, ripples in space-time itself, propagating outward at the speed of light. But all of this will happen without witnesses from Earth. The planet will be lifeless. The sun will still shine brighter than ever, illuminating a dead world, and the galaxy around it will be unrecognizable. The familiar spiral structure of the Milky Way, the band of light that stretches across the night sky, will be gone. The new merged galaxy, sometimes called Milkomeda or Milkdromeda, will be a different shape, a different structure, a different gravitational entity. The sun and its dead planets will orbit within this new galaxy, their position and trajectory altered by the merger, but likely still intact. There is a small chance, astronomically speaking, that the sun could be ejected from the galaxy entirely during the merger. Gravitational interactions can fling stars outward, and a certain percentage of stars in both galaxies will be cast out into intergalactic space. If the sun is one of them, it will drift through the void between galaxies, carrying its retinue of dead planets with it, isolated, alone, no longer part of any galactic structure. But this is unlikely. Most stars survive the merger. Most remain gravitationally bound to the new galaxy. The sun will probably remain within Milkomeda, orbiting the new galactic center, just another star among trillions. 4 billion years is long enough for all of this to happen. It is long enough for Earth to die, for the sun to brighten, for the galaxies to collide, for new stars to be born and die, for black holes to merge, for an entirely new galactic structure to form. And it is also long enough for something else, something harder to predict. If humanity survives, if our species or our descendants or our creations persist for even a fraction of that time, they will have changed beyond recognition. 4 billion years is long enough for evolution to produce forms of life utterly unlike anything that exists today. It is long enough for intelligence to spread across star systems, across galaxies, across the universe. It is long enough for civilizations to rise and fall thousands of times over, or it is long enough for extinction. Most species on Earth have gone extinct. Most lineages end. There is no guarantee that humanity, or anything descended from humanity, will still exist in 4 billion years. The timescale is so vast that survival seems almost irrelevant. Whether we persist or vanish, the galaxy will continue, Andromeda will approach, the merger will happen. The universe does not care about our survival, it does not pause for witnesses. This is the collision timeline. 4 billion years of approach, a billion years of merger, and then a new equilibrium. The process is slow by human standards, unimaginably slow, but it is inevitable. Gravity does not stop, the distance closes. The galaxies fall toward each other, patient, relentless, indifferent to what exists or does not exist within them. By the time the merger is complete, everything familiar will be gone. The Earth you know, the sky you see, the stars you recognize, none of it will remain. But the universe will continue, reshaping itself, creating new structures, moving forward through time without memory or regret. And all of this is set in motion now. Andromeda is already approaching. The timeline has already begun. 4 billion years from now feels distant, impossibly far, irrelevant to your life or your concerns. But it is not separate, it is not disconnected. It is the future that is already in motion, already determined, already underway. The collision is not a possibility, it is a certainty, and it is happening right now 110 kilometers per second at a time. Gravity operates across impossible distances. This is not intuition, it is not obvious. When you drop an object, it falls. When you throw a ball, it arcs downward and returns to the ground. Gravity feels local, immediate, something that acts on objects within arm's reach or within sight. But gravity does not stop at the horizon. It does not fade at the edge of the atmosphere. It extends outward, infinitely, growing weaker with distance but never reaching zero. Every massive object in the universe exerts a gravitational pull on every other massive object, no matter how far apart they are. Andromeda and the Milky Way are gravitationally bound to each other across 2.5 million light-years of space. This means that despite the enormous distance, despite the vast emptiness between them, the two galaxies are pulling on each other. They have been pulling on each other for billions of years. They will continue to pull on each other until they merge. The force is weak at this distance, incomprehensibly weak, but it is real, it is measurable, and it is strong enough to overcome the expansion of space itself. The universe is expanding. This is one of the fundamental discoveries of modern cosmology. Space itself is stretching, carrying distant galaxies away from each other. The farther apart two galaxies are, the faster they recede. This is not because the galaxies are moving through space, but because the space between them is growing. At large enough distances, galaxies recede from each other faster than the speed of light, not because they are moving faster than light, but because the space between them is expanding faster than light can cross it. This expansion is happening everywhere, at all scales, all the time. But it does not affect Andromeda and the Milky Way. The gravitational attraction between the two galaxies is stronger than the expansion of space at this distance. Gravity wins. The galaxies are not being carried apart, they are being pulled together. This means they are part of a gravitationally bound structure, a system where the mutual gravity of the objects within it is strong enough to hold them together against the expansion of the universe. The Milky Way and Andromeda, along with dozens of smaller galaxies, form what is called the local group. The local group is a collection of galaxies that will never be separated by cosmic expansion. They are bound together, destined to interact, destined eventually to merge into a single structure. This binding happened early in the history of the universe. When the galaxies first formed, they were close enough that their gravity could dominate over the expansion. As the universe expanded, the space between galaxy groups grew, but the space within each group did not. The local group remained coherent while the rest of the universe spread outward. Over billions of years, the distance between the local group and other galaxy groups has increased. The nearest large galaxy cluster, the Virgo cluster, is approximately 50 million light-years away, and it is receding from us due to cosmic expansion. Eventually, in the far future, All galaxy groups outside the local group will recede beyond the cosmological horizon, disappearing from view, unreachable even at the speed of a light. The local group will become isolated, alone in an expanding void, with no connection to the rest of the universe. But within the local group, gravity maintains contact. Andromeda and the Milky Way pull on each other. The smaller galaxies in the group, the Magellanic Clouds, the Triangulum Galaxy, dozens of dwarf galaxies, all orbit within the gravitational influence of the two largest members. The entire structure is a gravitational web, a network of attraction and motion, with every object influencing every other object. The calculations are complex. The orbits are not simple ellipses. They are chaotic, influenced by multiple gravitational sources, by tidal forces, by the distribution of dark matter. But the overall result is clear. The local group is bound, and nothing within it will escape. The force binding Andromeda and the Milky Way is determined by their masses and the distance between them. Newton's law of gravitation states that the force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. The masses are enormous. Each galaxy contains hundreds of billions or trillions of solar masses. The distance is also enormous, 2.5 million light-years. When you calculate the gravitational force between two such massive objects separated by such a vast distance, the result is still significant. It is not strong enough to pull them together quickly, but it is strong enough to pull them together eventually. And this force has been acting for billions of years. The galaxies have been falling toward each other since they formed. The approach is not new. It is not recent. It has been ongoing for most of the age of the universe. The current velocity of 110 kilometers per second is the accumulated result of billions of years of gravitational acceleration. The galaxies started far apart, nearly at rest relative to each other, and gravity has been pulling them together ever since. The closer they get, the stronger the force becomes. The stronger the force, the faster they accelerate. The process is gradual, but it is relentless. This raises a question about destiny. Are Andromeda and the Milky Way destined to collide, or is there some possibility of escape? The answer is that they are destined to collide. The gravitational binding energy of the system is too great. The velocities are too low. There is no mechanism that could separate them. They are falling toward each other, and barring some unforeseen event, a close passage by another massive galaxy, an interaction with a large dark matter structure, they will merge. The future is determined. The outcome is certain. Gravity has decided. But gravity is not a force in the way humans typically understand forces. It is not a push or a pull exerted by one object on another. It is a curvature of space-time. Mass bends the fabric of space and time around it, and objects moving through that curved space-time follow the straightest possible paths, which appear as curved trajectories to an outside observer. The Earth orbits the Sun not because the Sun is pulling on it, but because the Sun's mass curves space-time, and the Earth is following a geodesic, a natural path through that curved space. The same is true for Andromeda and the Milky Way. The two galaxies are moving through space-time curved by each other's mass, and their trajectories are geodesics, natural paths that bring them together. This means that the collision is not an accident. It is not a random event. It is the natural consequence of the initial conditions of the universe, the distribution of matter after the Big Bang, the slight overdensities in the early universe that grew into galaxies and galaxy groups. Andromeda and the Milky Way were always going to collide. The moment they formed within the same gravitationally bound region of space, their fates were linked. Gravity ensured it. Space-time geometry ensured it. The mathematics of general relativity ensured it. And yet, despite this certainty, the binding is invisible. You cannot see gravity. You cannot detect the force directly. You can only observe its effects. You see Andromeda approaching, measured by Doppler shift. You see the orbital motions of stars within galaxies, indicating the presence of mass. You see the lensing of light around massive objects, bending as it passes through curved space-time. But gravity itself is not visible. It is not a thing you can point to. It is a property of space-time, a geometric feature, something fundamental to the structure of the universe but impossible to perceive directly. The gravitational bind between Andromeda and the Milky Way is also mediated by dark matter. Most of the mass in both galaxies is not in stars or gas. It is in dark matter halos, vast spherical distributions of invisible mass surrounding the visible galaxies. These halos extend far beyond the bright disks, reaching hundreds of thousands of light-years into space. The halos of Andromeda and the Milky Way may already be touching, overlapping, interacting gravitationally even though the visible parts of the galaxies are still millions of light-years apart. The dark matter does not emit light, does not absorb light, does not interact with electromagnetic radiation in any way. It can only be detected through its gravitational influence, but that influence is dominant. It outweighs everything else. The visible galaxies are embedded in dark matter structures, and those structures determine the dynamics of the system. This means that when Andromeda and the Milky Way collide, it will not just be a collision of stars and gas, it will be a collision of dark matter halos. The dark matter will pass through itself, because dark matter particles do not interact with each other except through gravity. The halos will merge, their combined mass forming a new, larger halo around the merged galaxy. The distribution of dark matter will change, the gravitational potential of the system will change, and the visible galaxies, the stars and gas that we can actually see, will respond to this new gravitational environment, settling into new orbits, new configurations, new equilibria. The gravitational bind is not just between Andromeda and the Milky Way, it is between all the galaxies in the local group. The Triangulum galaxy, the third largest member of the group, is also bound to the system. It may merge with Andromeda before Andromeda merges with the Milky Way, or it may merge with the combined system afterward. The smaller dwarf galaxies will also be affected. Some will be absorbed into the larger galaxies during the merger. Some will be ejected, flung outward by gravitational interactions, cast into intergalactic space. The final configuration of the local group after all the mergers are complete is uncertain, but the overall outcome is clear. Fewer galaxies, larger galaxies, a more consolidated structure. This is the fate of all gravitationally bound systems in an expanding universe. Over time, as the expansion carries unbound structures farther apart, the bound structures grow more isolated and more consolidated. Galaxy groups merge into single galaxies. Galaxy clusters evolve as their members interact and coalesce. The universe becomes emptier on large scales and denser on small scales. The expansion separates what is not bound, and gravity unifies what is bound. The local group is following this pattern. It is collapsing under its own gravity while the rest of the universe expands away. And this process is patient. It does not hurry. Gravity operates on timescales of billions of years. The binding has existed for billions of years. The collision will take billions of years. The final equilibrium will persist for trillions of years until the stars themselves begin to die and the galaxies fade into darkness. But throughout all of this, gravity remains constant, unchanging, acting across impossible distances, pulling objects together with a force that is weak but inexorable, invisible but undeniable. Andromeda and the Milky Way are bound together by gravity across 2.5 million light-years of space. This is not a temporary condition. It is not something that might change. It is the fundamental structure of the local group, the architecture of our corner of the universe, the destiny encoded in the distribution of mass and the curvature of space-time. The galaxies are falling toward each other because that is the only path available to them. Gravity has decided. The bind is absolute. Andromeda is not a solid object. It is not a wheel. It is not a disk. It appears as a unified structure when viewed from 2.5 million light-years away, a coherent spiral of light with defined arms and a bright central core. But this appearance is deceptive. Andromeda is a collection of individual stars, each one orbiting the galactic center independently, each one following its own path through space, each one moving at its own velocity. The galaxy has no surface. It has no fixed structure. It is a gravitational system, a dynamic assembly of objects held together by mutual attraction, constantly in motion, constantly rearranging itself. Stars near the center of Andromeda orbit faster than stars farther out, but not in the way you might expect. In a solid object like a spinning wheel, the outer edge moves faster than the inner portions because it has to cover a greater distance in the same amount of time. But galaxies do not rotate like solid objects. They rotate differentially. Each star orbits at a speed determined by the amount of mass interior to its orbit. Stars closer to the center, where more mass is concentrated, orbit faster. Stars farther out where the mass is more spread out, orbits slower. But the relationship is not simple, and it reveals something unexpected about the distribution of mass in galaxies. If a galaxy's mass were concentrated entirely in its centre, like a solar system, where most of the mass is in the Sun, then orbital velocities would decrease with distance according to Kepler's laws. The farther a star is from the centre, the slower it should orbit. This is true in our solar system. Mercury orbits the Sun at about 48 kilometers per second. Earth orbits at 30 kilometers per second. Neptune orbits at just 5 kilometers per second. The pattern is clear, velocity decreases with distance, but in galaxies this does not happen. When astronomers measure the orbital velocities of stars at different distances from the galactic centre, they find that the velocities remain roughly constant, or even increase slightly, far beyond the visible edge of the galaxy. Stars in the outer regions of Andromeda orbit at speeds similar to stars closer in, despite being much farther from the centre. This should not be possible if all the mass were in the visible galaxy. The only explanation is that there is additional mass, invisible mass, extending far beyond the visible stars. This is dark matter. The dark matter halo surrounding Andromeda contains more mass than all the visible stars combined, and it extends hundreds of thousands of light years into space, far beyond the bright spiral disk. This means that when a star in Andromeda's outer regions orbits the galactic centre, it is not orbiting just the visible galaxy. It is orbiting the entire mass distribution, including the dark matter. The dark matter does not emit light, does not form stars, does not interact with electromagnetic radiation, but it exerts gravity. It dominates the gravitational potential of the galaxy. Without it, the galaxy would not hold together. The stars in the outer regions would be moving too fast to remain bound. They would escape into intergalactic space, but they do not escape. They remain in orbit held by the gravity of the dark matter halo. The orbital period of a star in Andromeda depends on its distance from the centre. Stars near the core, where the density is highest, complete an orbit in tens of millions of years. Stars farther out, in the spiral arms, take hundreds of millions of years. Stars at the very edge of the galaxy may take 1 billion years or more to complete a single orbit. These are timescales far beyond human comprehension, far beyond the lifespan of any civilization, far beyond the entire history of complex life on Earth. A star in Andromeda's outer regions has completed only a handful of orbits since the galaxy formed. It has circled the galactic centre perhaps 10 or 20 times in the entire history of the universe. Each orbit is a journey of hundreds of thousands of light years, a slow drift through space guided by gravity, unnoticed, unremarked, simply one star among trillions following its assigned path. And as stars orbit, the structure of the galaxy changes. Spiral arms are not permanent features. They are density waves, regions where stars and gas are temporarily compressed as they move through a gravitational perturbation. The spiral arms you see in Andromeda are not made of the same stars over time. Stars drift into the arms, slow down as they pass through the denser regions, then drift out again on the other side. The arms themselves rotate, but at a different speed than the stars. This is called differential rotation, and it is responsible for the winding of spiral structure. The pattern persists, but the individual stars composing the pattern are constantly changing. This means that Andromeda's appearance is temporary. The spiral arms you see now are not the same spiral arms that existed 1 billion years ago. They are not the same spiral arms that will exist 1 billion years from now. The structure is dynamic, shifting, reforming. Stars are born in the spiral arms, where gas is compressed and star formation is triggered. Young, massive blue stars light up the arms, making them visible. But those stars are short-lived. They burn brightly for a few million years and then explode as supernovae. The arms fade and reform elsewhere as the density waves propagate through the disk. The galaxy is never static. It is always evolving. The motions of individual stars are even more complex. Stars do not orbit in perfect circles. They follow elliptical paths, oscillating in and out from the galactic centre, bobbing up and down above and below the galactic plane. A star in Andromeda might be near the edge of the visible disk at one point in its orbit, then swing inward toward the denser central regions, then move back outward again. It might rise hundreds of light years above the plane of the galaxy, then fall back down, crossing through the disk and emerging on the other side, only to be pulled back again by gravity. The motion is periodic but chaotic, influenced by the gravitational pull of nearby stars, by passing molecular clouds, by the overall potential of the galaxy. No two stars follow exactly the same path, and yet, despite this chaos, the galaxy maintains a coherent structure. The overall shape persists, the spiral pattern persists, the central bulge remains intact. This is because the motions are statistical. Individual stars move unpredictably, but the collective behavior of trillions of stars averages out into a smooth, organized system. This is similar to how gases behave. Individual gas molecules move randomly, colliding with each other, changing direction constantly. But the overall behavior of the gas, its temperature, pressure, density, follows predictable laws. Galaxies are the same. They are systems where individual chaos gives rise to collective order. The timescale of this motion is what makes it invisible. If you could watch Andromeda for 1,000,000 years, you would see the spiral arms slowly rotate. You would see stars drift through the arms, entering and exiting, brightening and fading. You would see new stars born and old stars die. You would see the structure shift, evolve, change. But you cannot watch for 1,000,000 years. You can only see a single snapshot, a frozen moment in time. The motion is real, but it is hidden by the limits of human perception. This is true for all galactic motion. The Milky Way is also rotating. The Sun orbits the galactic center at approximately 230 kilometers per second, completing one orbit every 225 million years. This is called a galactic year. In the time since dinosaurs first appeared on Earth, the Sun has completed less than one full orbit around the galaxy. In the time since the formation of Earth, the Sun has orbited roughly 20 times. These are the timescales on which galactic structure changes. Not days, not years, not centuries, but hundreds of millions of years. And within Andromeda, the same process is happening. Stars are orbiting, gas clouds are moving, the spiral arms are rotating, the structure is evolving. None of it is visible on human timescales, but all of it is real. The galaxy is not static. It is a dynamic, evolving system, constantly in motion, constantly rearranging itself under the influence of gravity. The stars you see in Andromeda's spiral arms will not be there in 100 million years. They will have drifted elsewhere, replaced by other stars entering the arms from different regions of the galaxy. The pattern will look similar, but the components will be different. This internal motion also affects the eventual collision with the Milky Way. When the two galaxies merge, the stars will not simply blend together. They will interact gravitationally. Their orbits will be disrupted. Stars that were moving in organized circular paths around their respective galactic centers will be flung into chaotic elliptical orbits. Some will gain energy and be ejected from the merged system entirely. Some will lose energy and sink toward the center. The orderly rotation of both galaxies will be destroyed, replaced by random motion. The spiral structure will be erased. What remains will be an elliptical galaxy, a smooth, featureless distribution of stars with no organized rotation, only random velocities. But this destruction is still billions of years away. For now, Andromeda rotates, its stars orbit, its spiral arms turn. The galaxy maintains its structure, held together by gravity, shaped by motion, evolving slowly across timescales that dwarf human history. The motion is invisible, but it is constant. Every star in Andromeda is moving, every gas cloud is drifting, every structure is shifting. The galaxy is not a thing. It is a process, a system, a collection of objects in motion, bound together by gravity, rotating through space, following paths determined billions of years ago when the galaxy first formed. And this motion will continue until the merger, until the collision, until the two galaxies fall together and the internal motion of both is transformed into chaos, until the rotation stops and the structure dissolves, until everything changes. But for now, Andromeda rotates, patient and slow, 1 trillion stars moving in silence, unseen, across distances and timescales that human minds cannot grasp. Measuring the distance to Andromeda is not a simple task. You cannot send a spacecraft there and measure the travel time. You cannot stretch a measuring tape across 2.5 million light-years of space. You cannot use parallax, the apparent shift in position of an object when viewed from different angles. because even from opposite sides of Earth's orbit around the Sun, Andromeda's position in the sky does not shift enough to measure. The distance is too vast. The tools that work for nearby objects fail completely when applied to something millions of light years away, and yet astronomers know the distance. They know it with reasonable precision. The value of 2.5 million light years is not a guess. It is the result of careful observation, mathematical calculation, and a technique called the cosmic distance ladder, a series of overlapping methods that allow distances to be measured at progressively larger scales. Each rung of the ladder extends farther into space, building on the measurements from the previous rung, until eventually you can reach objects so distant that direct measurement is impossible. The first rung is the most fundamental, measuring distances within the solar system. This can be done using radar. You send a radio signal to a planet, wait for it to bounce back, and measure the round-trip time. Since radio waves travel at the speed of light, you can calculate the distance. This works for nearby planets like Venus and Mars. Once you know the distances to other planets, you can use geometry and Kepler's laws to determine the size of Earth's orbit around the Sun. This distance, approximately 150 million kilometers, is called an astronomical unit, and it becomes the baseline for all further measurements. The second rung uses parallax. As Earth orbits the Sun, nearby stars appear to shift position relative to more distant background stars. The amount of shift depends on the star's distance. By measuring this shift, called parallax angle, you can calculate the distance using simple trigonometry. This works for stars within a few hundred light years. Beyond that, the parallax angle becomes too small to measure accurately, even with the most precise instruments. But within this range, parallax provides direct geometric measurements of stellar distances. It is the foundation on which everything else is built. The third rung involves something called standard candles, objects whose intrinsic brightness is known. If you know how bright an object actually is, and you measure how bright it appears from Earth, you can calculate its distance. The apparent brightness decreases with the square of the distance, so an object that appears 4 times dimmer is twice as far away. The challenge is finding objects whose intrinsic brightness is reliably known. For nearby stars measured by parallax, you can determine their actual luminosity by comparing their apparent brightness with their known distance. Once you know the luminosity of certain types of stars, you can use those stars as distance indicators. One of the most useful standard candles is a type of variable star called a Cepheid. Cepheids are massive, luminous stars that pulsate regularly, brightening and dimming over periods of days or weeks. In the early 20th century, astronomer Henrietta Swan Leavitt discovered that the period of a Cepheid's pulsation is directly related to its intrinsic luminosity. Longer period Cepheids are more luminous. Shorter period Cepheids are less luminous. This relationship, called the period luminosity relation, allows you to measure a Cepheid's pulsation period, determine its intrinsic brightness, compare that to its apparent brightness, and calculate its distance. Cepheids are bright enough to be seen in nearby galaxies. In the 1920s, Edwin Hubble used the newly constructed 100-inch telescope at Mount Wilson Observatory to resolve individual stars in what was then called the Andromeda Nebula. Among those stars, he identified Cepheid variables. He measured their pulsation periods, used the period luminosity relation to determine their intrinsic brightness, and calculated their distances. The result was astonishing. The Cepheids in Andromeda were far more distant than any star in the Milky Way. They were so distant that Andromeda could not possibly be a nebula within our own galaxy. It had to be a separate galaxy entirely, an island universe, millions of light years away. This discovery fundamentally changed humanity's understanding of the cosmos. Before Hubble's measurement, the universe was thought to consist of a single galaxy, the Milky Way, surrounded by empty space. Andromeda and other spiral nebulae were assumed to be clouds of gas within our galaxy, perhaps forming new solar systems. Hubble's distance measurement showed that this was wrong. Andromeda was not a cloud, it was another galaxy. And if Andromeda was a galaxy, then the other spiral nebulae were also galaxies. The universe was vastly larger than anyone had imagined, filled with billions of galaxies, each one containing billions of stars, all separated by millions of light years of empty space. The distance Hubble calculated in the 1920s was not accurate by modern standards. His initial estimate was about 900,000 light years, less than half the currently accepted value. The error was due to an incomplete understanding of Cepheid variables. There are actually two types of Cepheids, with different period luminosity relations, and Hubble did not know this. Later, astronomers refined the calibration, corrected the measurements, and determined that Andromeda is approximately 2.5 million light-years away. But despite the initial inaccuracy, Hubble's method was sound. The principle was correct. The cosmic distance ladder worked. Beyond Cepheids, other standard candles extend the ladder farther into space. Type Ia supernovae are one of the most important. These are exploding white dwarf stars that reach a consistent maximum brightness, bright enough to be seen across billions of light-years. By measuring the apparent brightness of a type Ia supernova and comparing it to the known intrinsic brightness, astronomers can calculate distances to galaxies far beyond the reach of Cepheid measurements. This technique was used to discover that the expansion of the universe is accelerating, driven by something called dark energy. The discovery earned the 2011 Nobel Prize in Physics. Each rung of the distance ladder builds on the previous one. Parallax calibrates nearby stars. Nearby stars calibrate Cepheids. Cepheids calibrate more distant objects. Distant objects calibrate supernovae. Supernovae extend measurements to the edge of the observable universe. But every rung introduces uncertainty. Every step compounds errors. If the calibration of Cepheids is slightly wrong, then all distances measured using Cepheids are also wrong. If the assumption that type Ia supernovae have consistent brightness is incorrect, then distances to distant galaxies are uncertain. The ladder is only as strong as its weakest rung. This is why measuring distances in astronomy is difficult. It is not direct. It is not simple. It requires multiple steps, each one relying on assumptions and calibrations that must be constantly refined. Modern telescopes, particularly the Hubble Space Telescope, have improved these measurements dramatically. Hubble has observed Cepheids in galaxies tens of millions of light-years away, far beyond what ground-based telescopes can resolve. The James Webb Space Telescope, with its infrared sensitivity, is extending these measurements even farther, refining the distance ladder, reducing uncertainties, improving our understanding of cosmic distances. But for Andromeda, the distance is relatively well established. Multiple methods have been used. Cepheid variables provide one measurement. The brightness of the galaxy's stars provides another. The motion of the galaxy, its velocity, and its gravitational interactions with the Milky Way provide constraints. All of these methods converge on the same answer: approximately 2.5 million light-years. The uncertainty is small, perhaps a few percent. The distance is known, and knowing this distance changes everything. It transforms Andromeda from a faint smudge in the night sky into a comprehensible object. It allows you to calculate its size, its mass, its structure. It allows you to understand its motion, its approach, its eventual collision with the Milky Way. It places Andromeda within the larger context of the universe, as a member of the local group, as a gravitationally bound companion to our own galaxy, as an object whose fate is linked to ours. But the distance itself remains almost incomprehensible. 2.5 million light-years. Light, travelling at the fastest speed in the universe, takes 2.5 million years to cross the gap. Nothing human-made will ever travel that distance. No signal sent from Earth will reach Andromeda in any time frame that matters to human civilization. The distance is a barrier, an absolute separation, a reminder that the universe is larger than human ambition, larger than human capability, larger than human imagination. And yet, astronomers measured it. They built a ladder of techniques, calibrated each step carefully, extended their reach across millions of light-years, and determined the distance with precision. This is one of humanity's greatest intellectual achievements, not because it serves a practical purpose, but because it demonstrates the power of observation, mathematics, and reason. The distance to Andromeda is not useful. It does not improve your life. It does not solve problems. But it is knowable, and knowing it, truly understanding what it means, changes how you see the universe. The cosmic distance ladder extends far beyond Andromeda. It reaches to galaxies billions of light-years away, to the edge of the observable universe, to the limits of what can ever be seen. Each rung extends farther, each measurement more uncertain, but the principle remains the same: build on what you know, use reliable methods, refine constantly, and slowly, step by step, measure the universe. Andromeda is just one rung on this ladder, but it is an important one. It is close enough to measure accurately. It is large enough to study in detail. It is the bridge between the local and the cosmic, between what can be seen clearly and what can only be inferred. And its distance, 2.5 million light-years, is both a number and a revelation. For most of human history, Andromeda was invisible. Not because it was not there, not because it was too faint, but because humans did not know how to see it. The light was always reaching Earth. The photons were always striking human eyes. But the conditions required to notice a faint smudge of light in the night sky, dark skies, clear air, deliberate observation, were rare. Most people lived under conditions that made seeing Andromeda difficult or impossible. During the day, sunlight overwhelmed it. At night, moonlight obscured it. Clouds blocked it. Firelight and torchlight destroyed night vision. Most humans throughout history never saw Andromeda, never knew it existed, never had reason to look for it, but some did see it. The earliest known written record of Andromeda comes from the Persian astronomer Abd al-Rahman al-Sufi in the year 964 CE. He described it as a small cloud in his Book of Fixed Stars, noting its position in the constellation Andromeda. He called it a nebulous smear, something distinct from the stars around it. Al-Sufi was working in an era of careful celestial observation, cataloguing stars, measuring positions, recording details that earlier astronomers had missed. He saw Andromeda because he was looking carefully, systematically, at every part of the night sky. He did not know what it was, he could not have known, but he recorded it, and that record survived. Other observers noticed it as well. Chinese astronomers may have observed it even earlier, though records are less clear. European astronomers in the medieval period noted its existence but offered no explanation. It was simply there, a faint patch of light. Unremarkable, unimportant, just another feature of the heavens. The invention of the telescope in the early 17th century allowed closer inspection, but telescopes did not immediately reveal Andromeda's nature. Through a telescope, Andromeda appeared larger, more detailed, but still cloud-like, still nebulous. It looked like a diffuse glow, not a collection of stars. Observers assumed it was exactly what it appeared to be, a cloud of gas or dust, a nebula, something within the Milky Way. This assumption persisted for centuries. As telescopes improved, as observational techniques became more sophisticated, Andromeda remained classified as a nebula. Astronomers catalogued it, measured its position, tracked its appearance, but did not question its nature. Charles Messier, the French astronomer who compiled a famous catalogue of nebulous objects in the 18th century, listed Andromeda as M31, the 31st entry in his catalogue. Messier's purpose was not to study these objects, but to identify them, so that comet hunters would not confuse them with comets. Nebulae were permanent fixtures in the sky. Comets moved. By cataloguing the nebulae, Messier helped others avoid wasting time on objects that were not comets. Andromeda was just one of many such objects, notable only for being bright and easy to see. By the 19th century, astronomers had begun to classify nebulae into different types. Some were clearly clouds of gas glowing because they were illuminated by nearby stars. Others were darker, appearing as voids against the background stars, likely clouds of dust blocking light from behind. But some nebulae, including Andromeda, had a distinct spiral structure. When photographed with long exposures, these spiral nebulae revealed intricate patterns of light, winding arms, bright cores, symmetrical shapes. They were beautiful, mysterious, and entirely unexplained. Two competing theories emerged. The first suggested that spiral nebulae were solar systems in the process of formation, clouds of gas and dust collapsing to form new stars and planets. This idea was appealing because it fit with emerging theories of how the solar system had formed. If our sun and planets condensed from a rotating cloud of material, then perhaps these spiral nebulae were other such clouds, observed at different stages of development. The second theory suggested that spiral nebulae were separate galaxies, distant collections of stars far beyond the Milky Way. This idea was more radical, implying that the universe was vastly larger than previously thought, filled with countless galaxies each containing billions of stars. The debate came to a head in 1920, in what is now called the Great Debate. Astronomers Harlow Shapley and Heber Curtis argued opposing views in front of the National Academy of Sciences. Shapley argued that spiral nebulae were relatively small and nearby, part of the Milky Way. Curtis argued that they were distant and massive separate galaxies. Both presented evidence, both made compelling arguments. But neither could definitively prove their case. The resolution required better observations, more precise measurements, a way to determine distances with certainty. That resolution came in 1924 when Edwin Hubble identified Cepheid variable stars in Andromeda. By measuring the periods of these Cepheids and applying the period-luminosity relation, Hubble calculated that Andromeda was approximately 900,000 light-years away, far beyond the boundaries of the Milky Way. The distance was later revised upward to 2.5 million light-years as the calibration of Cepheids improved, but the conclusion remained the same. Andromeda was not a nebula, it was not a cloud, it was not part of the Milky Way, it was another galaxy entirely, an island universe, a vast collection of stars separated from our own by an almost incomprehensible distance. This discovery fundamentally altered humanity's perception of the cosmos. Before Hubble, the universe was thought to consist of a single galaxy surrounded by emptiness. After Hubble, the universe became a place filled with galaxies, billions of them, each one a massive structure containing billions of stars, all separated by millions of light-years of space. The scale of the universe expanded overnight. What had been considered the entirety of existence became just one small part of a vastly larger whole. And Andromeda, the faint smudge that had been observed for centuries, suddenly became significant. It was not just another object in the sky. It was proof that the universe extended far beyond what anyone had imagined. It was the first galaxy outside the Milky Way to be definitively identified. It was the key that unlocked the realization that the cosmos was not small, not contained, not limited to what could be seen easily. The universe was vast, filled with galaxies, and Andromeda was the nearest example, the most accessible proof of this new understanding. But even with this knowledge, Andromeda's appearance did not change. It remained a faint smudge. It remained difficult to see without dark skies and clear conditions. It remained, to the casual observer, unremarkable. The revelation was intellectual, not visual. You could know that Andromeda was a galaxy containing 1 trillion stars, and it would still look like a small cloud. You could understand that it was 2.5 million light-years away, and it would still fit within the width of your thumb held at arm's length. The knowledge transformed perception, but it did not transform appearance. This disconnect between appearance and reality is central to understanding Andromeda. For most of human history, it was perceived as a minor feature of the night sky, something to note and catalogue but not to wonder about deeply. When telescopes revealed its spiral structure, it became more interesting, more beautiful, but still not extraordinary. Only when distance measurements revealed its true nature did it become significant. Only when humanity understood what it was looking at did Andromeda become important. And even now, centuries after Al-Sufi first recorded it, decades after Hubble revealed its distance, Andromeda remains largely unknown to most people. Many have never heard of it. Many who have heard of it have never seen it. Many who have seen it do not realize what they are looking at. The light reaches Earth every night, carrying information from 2.5 million years ago, but most of it goes unnoticed, unobserved, unremarked. The photons strike the atmosphere, scatter, or pass through, and only a tiny fraction enter human eyes. And of those who see it, only a few understand what they are seeing. This is the history of Andromeda's perception, from invisible, to noted, to catalogued, to misunderstood, to finally recognised for what it truly is. The progression took over 1,000 years. It required patient observation, careful measurement, intellectual courage, and the willingness to accept that the universe might be far larger and stranger than intuition suggested. And in the end, the discovery did not come from seeing something new. It came from understanding something that had always been there. Andromeda was always a galaxy. It was always 2.5 million light-years away. It contained 1 trillion stars. None of that changed when Hubble made his measurements. What changed was human understanding. What changed was the realization that a faint smudge of light could represent something so vast, so distant, so incomprehensibly large that it challenged every assumption about the nature of existence. And now, when you look at Andromeda, you see it differently than Al-Sufi did. You see it differently than Messier did. You see it differently than observers in the 19th century did. Not because it has changed, but because you know what it is. The light is the same, the appearance is the same, but the meaning has transformed, and that transformation is irreversible. Once you know that Andromeda is a galaxy, you cannot unknow it. Once you understand the distance, you cannot forget it. The perception has shifted permanently. Andromeda is enormous. It spans 220,000 light-years from edge to edge, more than twice the diameter of the Milky Way. It contains 1 trillion stars, each one a massive nuclear furnace generating light and energy. The total light output of Andromeda is staggering, billions of times brighter than the Sun, enough to illuminate a vast region of space around it. And yet, when you look at Andromeda from Earth, it appears tiny. It appears as a faint, narrow smudge barely visible to the naked eye, occupying less space in your visual field than a single bright star. This is the visibility paradox. Something immense appears small, something blindingly bright appears dim. The disconnect between what Andromeda is and what it looks like is so extreme that it borders on incomprehensible. The reason for this paradox is distance. Andromeda is 2.5 million light-years away, and at that distance, even something as large as a galaxy is compressed into a tiny patch of sky. Angular size, the measure of how large an object appears from a given distance, decreases with distance in a straightforward way. The farther away something is, the smaller it looks. This is intuitive for nearby objects. A mountain looks large when you stand at its base, but shrinks to a small bump on the horizon when viewed from 100 kilometers away. But the effect becomes counterintuitive when applied to truly distant objects, because the size of the object and the distance to it are both so far outside human experience that the mind cannot reconcile them. Andromeda's angular size in the sky is approximately 3 degrees, roughly 6 times the width of the full moon. If your eyes were sensitive enough to detect all of Andromeda's light, if you could see the faint outer regions of the galaxy that normally remain invisible, Andromeda would dominate the autumn sky. It would stretch across a significant portion of your view, a vast glowing oval, bright enough to be impossible to ignore. But your eyes are not that sensitive. You see only the brightest central region, the core where star density is highest, where the light is concentrated. The rest of the galaxy fades below the threshold of human vision. What should appear as a massive structure appears instead as a barely noticeable smudge. This selective visibility creates a false impression. When you see Andromeda, you're not seeing the whole galaxy. You're seeing perhaps 10% of it, maybe less, depending on observing conditions. The spiral arms, the outer regions, the faint halo, all of this is invisible to the naked eye. A telescope reveals more, capturing light too faint for human eyes to detect, showing the full extent of the galaxy. Long exposure photographs reveal even more, integrating light over minutes or hours, bringing out details that no visual observation could ever show. But even these images do not show everything. The dark matter halo, which contains most of Andromeda's mass, remains completely invisible. It does not emit light. It does not reflect light. It cannot be photographed. It can only be inferred. The paradox deepens when you consider brightness. Andromeda is one of the most luminous objects in the night sky, brighter than all but a handful of stars. The total amount of light reaching Earth from Andromeda is substantial, enough that if it were concentrated into a point source like a star, it would be easily visible, perhaps even one of the brightest stars in the sky. But the light is not concentrated. It is spread out across 3 degrees of sky, diluted across a large area, reduced to a faint glow. The total light is high, but the surface brightness, the amount of light per unit area, is low. This is why Andromeda appears faint despite being intrinsically bright. The light is there, but it is diffuse. This diffusion also makes Andromeda vulnerable to light pollution. A star, being a point source, remains visible even in moderately light-polluted skies. Its light is concentrated, and the eye can detect it against the background glow of artificial lights. But Andromeda's light is spread out, and when the sky itself is glowing from scattered city lights, the contrast between Andromeda and the background disappears. The galaxy fades into invisibility. In a city, Andromeda cannot be seen at all, not because it is not there, not because its light is not reaching you, but because the background is too bright. The visibility of Andromeda depends not just on the galaxy itself, but on the darkness of the sky around it. This means that for most of human history in most places Andromeda was more visible than it is today. Before electric lighting, before cities grew large and bright, the night sky was darker. Andromeda was easier to see, more prominent, more likely to be noticed by casual observers. The invention of artificial lighting has made the galaxy invisible to billions of people. It is still there, still emitting the same light, still occupying the same position in the sky, but the conditions required to see it no longer exist for most of humanity. The visibility paradox has become more extreme over time. The galaxy has not changed, but human ability to perceive it has diminished. Another aspect of the paradox involves perspective. Andromeda's true size, its physical diameter of 220,000 light-years, is a measurement in space. But when you observe it from Earth, you are measuring angular size, a projection onto the sky. These two measurements are related but not equivalent. An object can be physically enormous and still appear small if it is far enough away. And an object can appear large in angular terms and still be physically small if it is close enough. Andromeda is both physically large and far away, and the result is an angular size that, while not negligible, is small enough to be easily overlooked. If Andromeda were closer, the angular size would increase dramatically. If it were half as far away, it would appear twice as large. If it were 1/10 as far away, 250,000 light-years instead of 2.5 million, it would span 30 degrees of sky, stretching from horizon to zenith, utterly dominating the night. The stars within it would be individually visible. The spiral structure would be obvious. The galaxy would be impossible to ignore. But it is not closer. It is exactly where it is, 2.5 million light-years away, and at that distance, even something as large as a galaxy becomes a faint smudge. The paradox also applies to individual stars within Andromeda. Each star in the galaxy emits light, and that light travels across 2.5 million light-years to reach Earth. But from this distance, individual stars are not visible. Even the brightest stars in Andromeda, massive blue supergiants thousands of times more luminous than the Sun, are too faint to be resolved without powerful telescopes. The light from 1 trillion stars blends together into a diffuse glow. You see the galaxy as a whole, but you do not see the components. The stars are there, each one shining, each one contributing to the total light, but they are invisible. The galaxy is an aggregate, a sum, a collective glow created by objects you cannot individually perceive. This is true for all distant galaxies, but it is especially striking for Andromeda because Andromeda is close enough that it should, in principle, be resolvable into stars. The technology exists. The Hubble Space Telescope has imaged regions of Andromeda in extraordinary detail, resolving millions of individual stars, showing the structure of star clusters, revealing the distribution of young and old stellar populations. But this requires a space-based telescope with exquisite sensitivity, long exposure times, and careful processing. To the naked eye, or even to a small backyard telescope, Andromeda remains a blur, a glow, a smudge. The individual stars are inaccessible. The visibility paradox is not unique to Andromeda, but Andromeda is the clearest example of it. Most galaxies are too far away to see at all without a telescope. Most galaxies are so distant that even powerful telescopes show them only as faint smudges. But Andromeda is visible to the naked eye, just barely under the right conditions. It is on the edge of human perception, occupying a liminal space between the visible and the invisible. If it were slightly farther away, it would be invisible. If it were slightly closer, it would be obvious. It exists at exactly the distance where it can be seen, but only barely, only if you know where to look, only if the conditions are right. This makes Andromeda frustrating. You know it is there. You know it is enormous. You know it is bright. But when you look at it, you see almost nothing. A small patch of light, easily missed, easily dismissed. The knowledge and the perception do not align. The intellectual understanding and the visual experience are completely disconnected. You can know that you are looking at 1 trillion stars, and it will still look like a faint cloud. You can understand that the galaxy spans 220,000 light-years, and it will still fit within the width of your thumb. The paradox cannot be resolved, it can only be acknowledged. And this paradox is a reminder that the universe does not care about human perception. Objects are not sized or positioned or brightened for our convenience. Andromeda is where it is, how it is, regardless of whether we can see it clearly. The fact that it appears small does not make it small. The fact that it appears faint does not make it faint. The appearance is an accident of distance, an artifact of perspective, a consequence of geometry and light, and the limitations of human eyes. The reality is unchanged. Andromeda is enormous. Andromeda is bright. And Andromeda is invisible to most people who have ever lived. Andromeda is our nearest major galactic neighbour, and we will never speak to it. This is not a metaphor. It is not poetic exaggeration. It is a simple consequence of distance and the finite speed of light. Communication requires the exchange of information, the transmission of a signal from one location to another, and the reception of a response. On Earth, this happens nearly instantaneously. You speak and someone hears you within milliseconds. You send a radio signal, and it arrives at its destination within fractions of a second. Even across planetary distances, communication is possible. Radio signals travel to Mars in approximately 20 minutes. Messages sent to the Voyager spacecraft, now beyond the edge of the solar system, take over 20 hours to arrive. The delays are noticeable, but the communication is real. You can send a signal and eventually receive a response. But Andromeda is not in the solar system. It is not even in the same galaxy. It is 2.5 million light-years away, and at that distance, communication becomes meaningless in any practical sense. A radio signal sent from Earth toward Andromeda would travel at the speed of light, the fastest speed possible in the universe, and it would take 2.5 million years to arrive. If someone in Andromeda were listening, if they received the signal and immediately sent a response, that response would take another 2.5 million years to return to Earth. The total round-trip communication time would be 5 million years. 5 million years ago, Earth was in the Pliocene epoch. Early hominids had not yet evolved. Australopithecus, the genus that would eventually give rise to humans, had just begun to appear. The continents were in different positions. The climate was different. Ice ages had not yet begun. If a signal had been sent from Andromeda at that time, travelling at the speed of light, it would be arriving at Earth now today, carrying information about Andromeda as it existed 5 million years ago. And if we sent a response today, it would not reach Andromeda until 5 million years from now, when Earth, humanity, and everything familiar will likely be gone. This makes communication impossible, not difficult, not impractical, impossible. There is no technology, no method, no theoretical framework that can overcome this barrier. The speed of light is absolute. Nothing can travel faster. Information cannot be transmitted faster. No signal can cross 2.5 million light-years in less than 2.5 million years. The delay is not a limitation of current technology. It is a fundamental property of the universe. Even if humanity developed the ability to send powerful, focused signals across intergalactic distances, even if Andromeda contained civilizations capable of receiving and responding to those signals, the conversation would still take 5 million years per exchange. By the time a response arrived, the civilization that sent the original message would almost certainly no longer exist. This enforced silence is absolute. Andromeda is visible. You can see it. You can observe it. You can study its light, measure its motion, calculate its mass, analyze its structure, but you cannot communicate with it. The light you see is information, yes, but it is one-way information. It tells you what Andromeda was like 2.5 million years ago. It does not tell you what Andromeda is like now, and there is no way to know what Andromeda is like now. The present moment in Andromeda is inaccessible. It is hidden behind a barrier of time, separated from you by the speed of light and the vastness of space. This separation applies to everything in Andromeda. If there are planets orbiting stars in that galaxy, you cannot know about them in real time. If there are civilizations, you cannot detect them as they currently exist. If a star exploded in Andromeda yesterday, you will not see it for another 2.5 million years. The galaxy you observe is a ghost, an image, a historical record. The actual galaxy, the one that exists right now, is unknowable, and it will remain unknowable until the light from the present moment in Andromeda finally reaches Earth 2.5 million years from now. By then, the present will have become the past. The cycle continues. The separation is permanent. And this separation is not unique to Andromeda. It applies to all distant objects. The farther away something is, the farther back in time you are seeing it, and the longer it would take to communicate. Galaxies billions of light years away are visible, but only as they were billions of years ago. The universe you observe is a patchwork of different times, with nearby objects appearing nearly as they are now, and distant objects appearing as they were in the ancient past. There is no universal now. There is no shared present moment. Every object exists in its own slice of time, separated from every other object by the light travel time between them. This creates a strange kind of loneliness. Andromeda is there. It is real. It contains 1 trillion stars, possibly trillions of planets, perhaps life, perhaps intelligence, perhaps civilizations. But you are separated from all of it by an unbridgeable gap. You can look, but you cannot touch. You can observe, but you cannot interact. You can wonder, but you cannot know. The galaxy is visible but unreachable, present but silent, nearby but impossibly distant, and the silence is mutual. If there are observers in Andromeda looking back at the Milky Way, they face the same barrier. They see the Milky Way as it was 2.5 million years ago. They see a galaxy populated by early hominids, by species that would eventually give rise to humans but had not yet done so. They cannot see cities, they cannot detect radio signals, they cannot know that intelligence has arisen in the Milky Way because the light carrying that information has not yet reached them. From their perspective, the Milky Way is silent, primitive, lifeless, and if they send a signal toward us, we will not receive it for 2.5 million years. By the time it arrives, we may no longer exist to hear it. This enforced silence also means that the universe is more isolated than it appears. When you look at the night sky and see thousands of stars, you might feel connected to the cosmos, part of a vast network of celestial objects. But the connection is illusory. You're not connected to those stars. You're separated from them by distance and time. The light you see is old. The stars you observe may have changed. Some may no longer exist. And there is no way to check, no way to verify, no way to close the gap. You are observing a universe that is fundamentally disconnected, where every object is isolated in its own light cone, its own causally connected region of space-time separated from everything else by barriers of distance and time. Andromeda and the Milky Way are gravitationally bound. They are approaching each other. They will eventually merge. But even this connection is limited. The merger will take billions of years. The galaxies are falling toward each other now, but they cannot communicate. They cannot coordinate. They cannot exchange information. The collision will happen when it happens, determined by gravity and initial conditions, not by any interaction or communication between the two systems. The galaxies are like two objects falling toward each other in a vacuum, aware of each other only through the force pulling them together, unable to signal, unable to speak, unable to know anything about each other except what gravity reveals. And when the merger finally occurs, when the two galaxies collide and blend and form a new structure, the silence will continue. The stars from both galaxies will mix, their orbits randomized, their positions shuffled. But the stars themselves will not interact. They will pass through each other, separated by light years, never colliding, never touching. Even in the chaos of a galactic merger, the fundamental isolation persists. Objects remain separated. Communication remains impossible. The silence remains unbroken. This is the reality of neighboring silence. Andromeda is our closest major galactic neighbor, and yet it is completely inaccessible. We can see it. We can study it. We can measure it. But we cannot reach it, cannot speak to it, cannot know it as it currently exists. The distance is too great. The timescales are too vast. The universe does not provide a mechanism for closing the gap. The speed of light is finite, and the distances are infinite in practical terms. The result is silence, absolute and permanent, a reminder that the universe is larger and emptier and more isolated than human intuition can accept. Andromeda hangs in the night sky, a faint smudge of light, visible but untouchable, present but silent. It has been there for billions of years. It will be there for billions more, and throughout all of that time, from the moment the first light left its stars until the moment the galaxies finally merge, the silence will persist. We are neighbours only in the loosest sense of the word. We share a gravitational bond. We share a future collision. But we do not share a present. We do not share communication. We do not share connection. We are separated by 2.5 million light years, and that separation is absolute. Andromeda is a galaxy. This is a simple statement, a basic fact, something you could find in any textbook or encyclopedia, but understanding what it means, truly grasping the implications of that statement, requires more than memorizing a definition. It requires confronting the scale of distance, the vastness of time, the incomprehensible numbers, the silence, the separation, the limits of human perception and human reach. Andromeda is not just a galaxy. It is a reminder of how small you are, how brief your existence is, how limited your perspective remains, even when armed with knowledge and instruments and centuries of accumulated understanding. You can see Andromeda with your own eyes. On a clear night far from city lights, you can look up and find that faint smudge of light in the constellation Andromeda. The photons entering your eyes have travelled for 2.5 million years to reach you. They left a galaxy containing 1 trillion stars, crossed an emptiness so vast that human minds cannot truly comprehend it, and arrived at the small aperture of your pupil. Most of the photons emitted by Andromeda never reach anything. They travel outward forever, expanding into the void, destined to pass through empty space for eternity. But a few reach you, and in that moment, you're connected to something ancient, distant, and impossibly large. But the connection is not what it appears to be. You're not seeing Andromeda as it is. You're seeing Andromeda as it was, long before your species existed, long before intelligence arose on Earth, long before anything you would recognize as familiar. The galaxy you observe is a ghost, a memory, an image preserved in light. The actual galaxy, the one that exists now at this very moment, is unknowable to you. It is hidden behind the speed of light, separated by time as much as by distance. You will never see the present-day Andromeda. You will never know what is happening there right now. The barrier is absolute. And yet, Andromeda is our neighbour. It is the closest large galaxy to the Milky Way. If this is what close means on a cosmic scale, then the universe is far more empty, far more isolated, far more lonely than human intuition suggests. The word neighbour implies proximity, connection, the possibility of interaction. But there is no interaction across 2.5 million light years. There is no communication. There is only observation, one way and delayed, looking backward through time at something you can never reach. Andromeda spans 220,000 light years across. It contains 1 trillion stars. It is approaching the Milky Way at 110 kilometers per second, destined to collide in 4 billion years. These are facts. These are measurements. These are numbers you can write down, calculate with, use in equations. But the numbers do not convey the reality. They do not make you feel the scale. They do not bridge the gap between intellectual understanding and visceral comprehension. You can know all of this and still look at Andromeda and see only a faint smudge, still feel nothing, still fail to grasp what you're actually looking at. This is not a failure of knowledge. It is a limitation of perception. Human minds did not evolve to understand distances measured in millions of light years. Human intuition does not operate on timescales of billions of years. Human senses cannot perceive 1 trillion of anything. You're equipped to understand your immediate environment, to navigate terrain, to interact with objects within reach, to survive in a world measured in meters and seconds and countable quantities. The universe operates on different scales entirely, and those scales exceed your cognitive capacity. You can learn the facts, you can understand the mathematics, but you cannot truly feel what it means. And perhaps that is appropriate. Perhaps the universe is not meant to be felt. Perhaps it simply is, indifferent to whether you understand it, indifferent to whether you can grasp its scale, indifferent to your existence entirely. Andromeda does not care that you are observing it. It does not care that you have measured its distance, calculated its mass, predicted its collision with your galaxy. It continues to exist, continues to rotate, continues to approach, completely unaffected by your awareness or your understanding. But you are affected. Knowing about Andromeda changes something. It shifts perspective. It makes Earth feel smaller, human concerns feel more temporary, individual life feel more fleeting. This is not a comfortable feeling. It is not reassuring. But it is honest. You are small. Your life is brief. Your species is young. Your planet is one of trillions. Your galaxy is one of hundreds of billions. And Andromeda, the closest major galaxy, is still so far away that you will never reach it, never communicate with it, never know it as it truly is. And yet, You can still look. You can still observe. You can still measure and calculate and understand, even if that understanding is incomplete, even if it is limited, even if it leaves you feeling smaller and more isolated than before. The act of looking outward, of seeking to understand something far beyond your reach, is itself significant. It is a recognition that the universe extends beyond you, that there are things larger and older, and more vast than anything in your immediate experience. It is an acknowledgement that human perspective is limited, that intuition fails, that the cosmos operates on terms that have nothing to do with you. Andromeda will continue to approach. The distance will continue to close. In 4 billion years, the galaxies will merge and everything familiar will be transformed. But you will not see it. No one alive today will see it. No one who remembers Earth as it currently is will see it. The collision is inevitable, but it is not for you. It belongs to a future so distant that it might as well be infinite. For now, Andromeda remains where it has always been. A faint smudge in the autumn sky. A neighbour that is not truly close. A galaxy visible to the naked eye but incomprehensible to the human mind. You can see it. You can know about it. You can understand what it represents. But you cannot change the distance. You cannot close the gap. You cannot make it anything other than what it is. Vast, distant, silent, and ultimately unreachable. And somehow that makes it more significant, not less.